Hello everyone, welcome to Masonry Design Requirements. In this lecture we're going to do two parts again. It'll be advantages and disadvantages of masonry structure and modes of structural failure in part 1, and then design properties of materials and performance requirements for design. That's going to be part 2. So in part 1 we're going to talk about advantages of masonry structure. As discussed before, masonry structure has immense durability. It's very strong and it can resist a lot of different weathering forces. It is boldest and beautiful natural material, so it can be you can get masonry materials in many different colors and different forms, different textures. It has excellent thermal and acoustic properties. It is very good in thermal and situations where you have to retain heat or where you have to keep a cold cellar cold. So you're going to use concrete blocks, which is common if you see in if you want to see cold cellars, you'll see concrete blocks or masonry blocks used because it's a very good at retaining the cold in there. And again, it has very good acoustic properties, so it is noise cancelling. So you can use these in buildings where you have to want to cancel walls, or in between different condo units. They sometimes use masonry blocks or block walls just to cancel out acoustical properties. It is good resistance to fire and weather. Again, it compared to wood, this wood catches fire very easily. Where you have places where you need to have good fire prevention, you will use concrete masonry or brick masonry, especially in places such as where you have chemical factories or you need to have some fire prevention area. So it's very good to resist fire and weather. It is fast and cheap to build certain types of buildings. So it is for small load-bearing buildings. It is very fast to build this type of masonry structure. And you do not need regular maintenance. It's easy to maintain this type of structure. You do not suffer from normal durability problems like concrete, steel, and timber. So concrete, you have to every now and then you will see they have to do bridge rehabilitation because concrete deteriorates because of the sulfur in there. In the concrete mix, the concrete masonry blocks do not have the same problem. Reinforcement helps enhance structural properties of masonry, so you can have reinforced rebar used to reinforce the masonry. It can be used as load-bearing or non-load-bearing walls. So non-load-bearing walls is basically for architecture masonry. Load-bearing is to resist the vertical and lateral loading. Lateral loading is also the wind loading, and it has vertical loading is the permanent structures like roofs that are put on top, or slabs that are floors that support the floor. So these are some of the advantages of masonry construction. One advantage that I missed to include is the fact that it is very good in situations of earthquake. So in areas where which are prone to having much more earthquakes, this we use a lot of masonry structure. Areas also depends on the type of material that's available in your area. So in North America or in Northern Hemisphere, you have more wood construction because wood is cheaper and easily available. In the Southern Hemisphere, it's more you find brick is much cheaper and much used much more. So some of the disadvantages of masonry structure: labor is very expensive and requires a lot of labor to build this type of structure compared to other structures, because it's heavy blocks that have to be used. You have to mix the concrete, and you have to do the work in a specified. So you can't wait. The mortar cannot dry, so you have to do the work in certain time span. So you need a lot of labor to do this work. So that's one of the disadvantages of this construction technique. or construction material, as it requires a lot of labor. So areas where they have a lot of cheap labor, you'll see a lot of masonry structure. Areas where labor is more expensive, it is not as cheap, or you won't see as much masonry structure. Also, the skill of the labor is very important. I think that's the next. Quality control of masonry. It is very hard to have quality control with masonry because it's all based on the skill of the laborer. So if you have trained, skilled people, then you will have good masonry structure and they'll have good quality control. Because compared to concrete, concrete has a lot of tests in place. They have quality control at the plant, they have quality control testing on site. Then you can also take core samples, do testing on the core samples, and it will give you an equivalent idea of how much the strength has been reached. Compared to that, masonry structure we don't have those ability to do some certain tests. We just have to be we can see a few things, like if whatever is visible to the eye, some deficiencies that you can see, but other than that, it's all based on the skill of your laborer. Another disadvantage of masonry structure, because it's not one cohesive structure, if the mortar is not prepared properly, it is prone to cracking, and if the mortar is not in placed properly in the gaps, and your it's prone to cracking. Then these cracking structures can be fixed with grouting, but this is one of the disadvantages of masonry structure. Another disadvantage is the strength of masonry. Like concrete, it's good in compressive strength, but it's weak in tension. So its tensile strength is not that great. It's good for compressive strength, so it's used for pillars and columns and load-bearing walls. So it's that in that sense, it's a very useful material, or it is that functions the best in that sense. There are several other disadvantages of masonry, which include detailing, which is critical. So like we said, you need to have good skilled people, so they can include the expansion and trinket joints and dam proofing courses. Those are very important. Also has a problem with efflorescence, staining, and graffiti. Masonry is very difficult to clean because of the textured material, or you cannot wash it down that easy compared to concrete. So those are some of the disadvantages of masonry structure. Now, going into modes of structural failure, there are 6 main modes of structural failure. You have pure axial compression, you have buckling, you have shear failure, then you have horizontal or vertical bending, you have overturning and lateral instability, and then wall beam interaction. So pure axial compression is when a piece of concrete block or brick is tested in the lab, where it's loaded with to see how the brick is going to be. So you can see when the brick is loaded, it has tensile cracks that go vertically along this path. So under controlled laboratory conditions, the masonry brick fails with vertical splitting, so that you could see, if you go back, you can see you have this vertical splitting happening right there, and the masonry brick is failing in this structure. If you're testing a masonry brick which has mortar, so the mortar comes because of the vertical compression, the mortar tries to expand horizontally and it comes out. That's the first thing that happens, and then the brick starts to crack and induces tensile cracking. So this mode of failure by vertical splitting at right angles to the plane of the mortar occurs only in solid masonry. Face shell bedding hollow units fail by vertical splitting of their webs in the plane parallel to the member surface. So this happens even when they are loaded through concrete bond beams, which might otherwise be expected to hold them together. So you can see here what happens is when the force are applied on top and bottom, the brick or the masonry unit starts to split apart, and that's what brings the tensile cracks in the unit. Okay. And same with the mortar. So the first thing that happens is it compresses the two brick units, and the mortar starts expanding laterally and coming out. That's pure axial compression. Next is buckling failure. So buckling failure is when because of the loads from the top, the brick masonry bows out or tries to come. It moves out. You can see here it's coming out here, and here you can see it's bowing out again. Same here. They were trying to fix. This is actually another way of fixing the big brick buckling by putting meshes and plates to make it to make sure it doesn't fail. You can also see here at the window that the brick is bowing. So masonry walls are they're rarely subjected to pure in-plane compressive loads. So you always have some sort of eccentricity because of uneven loading. So that eccentricity and the excessive loading due to different situations, conditions, snow load, something, it pushes the masonry blocks out, and you have movement, and then there's failure somewhere in the middle wherever it's the weakest, right? So you'll see the outer face fails in vertical tension stresses followed by rigid body rotation of the blocks of masonry. It's most common in loading situation which have in-plane compressive loads and out-of-plane bending moment, right? So under either loading case, failure of the wall may occur by buckling. So either if it's eccentrically loaded or ineccentrically loaded, you will see the solid body rotation of the masonry blocks, and it just bends and goes inside or outside. So similar failures occur in slender concrete walls, or if the walls are very tall, you tend to have more failure in taller walls because of lack of support. Now, buckling failure also depends on the degree of rotational fixity and support at the edges of all of the walls. So depends on how many places this wall structure is supported. It is only supported at the top. If it's supported on all four sides, you will have double the amount of buckling, and supported on all four sides. And if it's a tall wall, it will buckle in a different method. So the type of support directly influences the effective length of the wall and its buckling direction. So for example, if its effective length of buckling is, if it's both ends are fixed, your effective length of buckling is 0.5 times the length. If both ends are pinned, your effective length is same as the length of the wall. And if one end is fixed and one end pinned, your effective length is 0.7 times your length. And if one end fixed and one end free, your effective length is 2 times your length. So that means that one end is completely free, and it's like a cantilever, right? So those are the different situations. Depending on that, you will have buckling failure occur. So the larger your effective length, the small buckling load, so it's vulnerable to buckling. So you have to somehow figure out to minimize your effective length by making it, either providing it supports or making shorter walls to avoid failure. Now, it's in practice the typical type of physical connection between the floors or roof and the masonry wall determine the support condition. There's two most common types of connection that are ideals for support conditions. So you have the timber beams. Now, the timber beams are connected via framing brackets to nailing plates, which are bolted into the masonry. So if these timber beams are bolted using plates, this is called a pinned ends. Comparatively, if you have concrete slab which is rigidly connected to the wall, these are called fixed ends. So you have a slab on top of a brick wall, and then the brick wall continues on top, then you have another slab, and then you continue on further. So that is called a fixed end. But if a timber beam is connected into one straight wall piece, those are called pinned ends. So the two will have different buckling failure, and So basically you're decreasing your effective length by using slabs instead of timber beam, either or case, but you're reducing the effective length for it to buckle. If masonry walls are provided with lateral support along vertical edges, in addition to horizontal edges, the restraint along the vertical edges may influence the buckling shape so that they can extend. It's called the two-way buckling mode. So if it's on both sides, you will have two-way buckling failure. So a very tall, narrow wall may be no more susceptible to buckling than a short wall if they have same width, if it's supported properly, right? That's the best thing, the case that we have to support the wall. So if it's going to be a tall wall, and if it has to be in an area where it's going to be susceptible to loading, additional loading, we have to provide supports. That's how we avoid buckling failure, and that's the situations for buckling failure. Next is shear failure. Shear failure, you can see in buildings where you have a lot of loading, it will shear along a diagonal, and you'll have compressive in one end and uplift in another. And you can see here, like it's the building is the wall has sheared diagonally. That's pretty common in shearing. It usually shears along a diagonal. So a modern building design, you have lateral wind loads, you have a fixed base for a shear wall, then you have tension from uplift and compression due to lateral loads, and then you have stresses, compression stresses due to dead loads of the structure itself. So in essence, the shear walls are large cantilevered beams. They're fixed at the base, and then they are free in the end and subject to uniform loading. So base fixity of the shear wall is achieved by a couple of forces, one in tension on the windward face and of the building, and in compression of the leeward face. So you'll have tension wherever there's upward in face, or it's called the windward face, and then on the leeward side, you'll have compression. So the overall stability of the building is then achieved by providing sufficient dead weight to ensure the tension does not occur at the leeward face. So we have to put enough dead weight that it does not just uplift itself in tension. So shear failure of walls loaded in their own plane may be due to one or more of the following modes. You have tension failure on the windward side. So you can see here this force acting here. You have uplift or tension failure, compression failure at the leeward face. So up here you have compression failure at the toe and it's crushing. So you're pushing the wall this way, so it's uplifting, and you have tension failure here, and because you're pushing the wall down that way, there's compression failure on the other side. Then the most common is the diagonal tension failure along the step line or sliding along the bed joints. So you'll see there is always along those bed joints, you'll see a diagonal tension failure. A certain amount of vertical compression increases the resistance to sliding, but however, compressive stresses is too great and the compression failure takes over. So you do have some compressive stresses that compression strengthens the resistance, but what happens is it eventually gives up and you will have these failures. So that's why when we go into design, we have to be careful depending on the wind loading in a certain area to avoid or reinforce the wall to avoid these kind of failures. Then you have horizontal or vertical bending. Masonry walls are subjected to lateral wind pressures that may fail in either horizontal bending or vertical bending, or a combination of both. So you can either have vertical bending, horizontal bending, or it's called two-way bending, like both actions are happening. So the type of failure mode depends on the support conditions of the horizontal or vertical edges and the strength of masonry in bending. The horizontal strength is only about 35% of the vertical strength, and that's why sometimes it happens less. So for horizontal bending, panels supported along its vertical edge bends in a horizontal plane. Most of the load, if not all, is carried by the horizontal spanning across between the vertical supports. Now you can have either two. There's two major kinds of failure: vertical bending and moments are usually negligible. Horizontal bending failure may be one of two types: either tooth failure, that means it happens on where your bends are or where joints are, right? So that's why it's called a tooth edge bend. Or vertical failure line, where the failure line is directly to the pre-bent joints of the masonry. So you go through all the joints and you have a bend there. So a tooth failure depends on the following characteristics of the wall: its adhesion between the mortar and the unit. So if there is the adhesion is not good, or the mortar is not good, you'll see it started to bend. The magnitude of vertical compressive stresses and the tensile strength of the masonry. So if, let's say, if the joints are not combined properly together and there's no reinforcement in the wall at that point, it might tend to bend, and the spacing of the perpends depend on the size and shape of the units. So it all depends on the size and shape of the unit, and it usually bends where there's no reinforcement. So to avoid this, if an area is prone to these kind of wind loading, we tend to put additional reinforcement. Vertical bending, similarly, a panel supported along the horizontal edge between two floors bends in a vertical plane. Most of the load, if not all, is carried by the vertical span acting between the horizontal supports. The vertical bending failure occurs as a hinge. So you can see, as a hinge, you just have a failure line and it starts to buckle and bend. The reason this is different, vertical bending is different from buckling. Buckling usually happens due to loads acting on the structure. Vertical bending happens from wind loads affecting laterally, impacting laterally on the wall. Then you have the two-way bending. If masonry wall is subjected to lateral pressures, is supported on more than one side. So if you're supported on either one or more sides, then you will find that it will have both horizontal and vertical bend, and you will kind of fold in the middle. Then you have the overturning and instability failure, where masonry walls, particularly freestanding walls like property walls or garden walls, are left are not protected properly or do not have the proper structure. It usually falls over. So you can see here, this property wall has too much overburden pressure, and it was not built to withstand that overburden pressure, or was not supported properly with either a buttress or a column. That's why you can see it's bending or leaning over. So you can have overturning or instability. Another example of these, this is if walls during construction, if walls are left freestanding on construction sites, awaiting lateral supports from the top and bottom floor. Sometimes due to heavy winds, you can see them blow over due to strong winds, right? So that's also another thing that we have to take into fact, that that's another failure mode that can happen. Another one is a wall beam interaction. That usually happens where you have lintels or beams. This is due to the action of the material above the lintel or the beam. So when steel or concrete beams support masonry walls, a complex interaction happens between the wall. The arching action develops in the wall. So you have an arching action of a triangular arching action that is happening on top. So compressive stresses in the wall are concentrated and intensified near each end. That can present a real problem if the top of the wall is already heavy loaded. So the stiffer the beam, the less the arching effect, so you won't have that arching effect. The beam needs to be very stiff to affect this significantly. So this is another thing that we have to take into account when we're designing with openings with beams or lintels. We have to make sure the action or the loading on top of those beams and lintels, how would it impact that the opening or the bending action. So arching action of the course is greatly affected by pressure of the wall openings, and cracking usually occurs between 45 and 60 degrees to the horizontal, extending from the supports towards the center of the beam. So you can see this arching action here, and then the bending of the beam. And this usually happens between a 45 and 60 degree angle. So there's a triangle on top. We use that to calculate the arching action onto the beam or the lintel below. So the load on the beam becomes triangularly distributed with a peak value at the midspan. So here you'll see this midspan is going to be the peak value of it. And then you have the magnitude reduction factor that we use, WL square over 8. And for deflection, WL 5, WL 4 divided by 384 EI. So those are the formula for strength and surfaceability. And we use that to check the wall beam interactions. Next is the design properties for materials. We will go over that in this next portion of the slides. Thank you.